Hello, this is Brother Cromer from the Math Department, and I'll be covering Lesson 20, which is dealing with test of independence. So here's the outline for these videos. First of all, I'll be reviewing a few items, followed up by hypothesis testing, and then wrapping up with checking requirements and descriptive statistics. Notice here that there is nothing about confidence intervals. There's no confidence intervals when we're dealing with test of independence. Okay, so first of all, let's review. This here represents a flow chart or a flow diagram of all the things that we've covered in Unit 2 and Unit 3. I'm bringing this up because for the next test, anything in Unit 2 and Unit 3 is fair game, with Unit 3 being more of an emphasis. But let's review a little bit what we've seen in Unit 2. Unit 2 is when we gathered quantitative data. Now there were three different options when we dealt with quantitative data. One was where we gathered one sample, then two samples, and then more than two samples or 3+ samples. Within one sample, we either knew the standard population standard deviation or we didn't. Okay, and then if we knew the population standard deviation, we did the one mean standard deviation known test using the z distribution. If we didn't know the population standard deviation, it is the one mean standard deviation unknown test, where we use the t distribution. Okay, with two samples is either dependent or independent samples. If it was dependent, that means how we took our second sample was dependent on how we chose our first sample. Okay, and if that's the case, we would have a matched pairs test. If the second sample selected is independent of how the first sample was selected, then we do a two independent samples test. Now, if we have 3+ samples, we have what's called ANOVA, and then so that's Unit 2. Now, Unit 3. Talking about Unit 3, this is what we've covered recently. So this here is we either have one sample or two samples. Now one sample, say for instance you want to find out the number of BYU Idaho students that like listening to Taylor Swift, it's either a yes/no response. We could do a one proportion test. Or maybe we want to do a two sample or two proportion test where we want to compare between men and women the percentages of those that like listening to Taylor Swift. Now what we're covering today is when we deal with a row and a column, or row and column variables. It says row and column table because it'll be listed in a table, but a row and column variable, we want to test to see if they are independent. They're two categorical variables. We want to test to see if they're independent. So that's what we're covering today, is test of independence. Okay, so then the next slide is, here's an example of a row variable and a column variable. We have, for instance, this is an analysis where we were comparing men and women to see whether or not they use labels when buying clothes. So the row variable is label user, whether or not they use it or don't, and then it's gender. Women or men would be your column variable. Now you can also use this data for a two proportion test. Okay, but I put this table up here on purpose because when you do a two proportion test, you're only limited to two row categories and two column categories. If you had more than two row categories or two column categories, then you wouldn't be able to use a two proportion test. Okay, but we can do with the test of independence. It's less limiting because we can have more than two rows and more than two columns. Okay, to be able to do our test. Now we're limited still because we have certain requirements that need to be met when doing a test of independence. But suffice to say is that we can have more than two rows and or more than two columns. Okay, so now the next thing is let's deal with is a hypothesis test. Now with the test of independence, there are 6 steps to doing the hypothesis test. Step 1 is state the null and alternative hypotheses. And so the null is that the row variable and the column variable are independent. And the alternative is that those two variables are not independent. Okay, that's step number 1. Now step number 2 is calculate. It looks like an X, but it's the Greek letter chi, C-H-I. Some of you might be tempted to say chi, but it's not chi, it's the Greek letter chi. So it's the chi-squared test statistic. And here's the formula for this. I don't want to dive too much into how that formula is calculated, but suffice to say I bring this up because if the observed count and the expected count in each of the cells, if there's a wide margin, that's going to be a bigger number for this test statistic, and so we are going to reject the null hypothesis. The expected count, what that means, in fact, let me go down a couple of slides here. The expected count is what we expect in each cell, assuming independence, assuming the null hypothesis is true, assuming independence between the row and column variables. If you're curious about how to calculate the expected count, is that you take the row total for a certain row times the column total for a given, it's the row total for a given cell times the column total for a given cell divided by the complete table total. If you're curious about do that, you're not You're not expected, though, to figure out how to calculate the expected counts. Okay. So then step number 3 is to determine the degrees of freedom. So the degrees of freedom is r minus 1 times c minus 1. R represents the number of rows in a table, and c is the number of columns. Then calculate the p-value. And then the last 2 steps are similar steps to what we've seen before. We reject the null if the p-value is less than the level of significance. If not, then don't reject, and then we state our conclusions in layman's terms. If we reject the null, we have sufficient evidence, and then we state the alternative hypothesis in English. If we don't reject, then we have insufficient, and then we state the alternative hypothesis in English. Okay, so let's go through one example. There was a recent survey taken on whether, and this is going back to the table that I referred to before, there were a recent survey taken on whether consumers are label users who pay attention to label details when buying clothes. Are men and women equally likely to be label users? Determine if gender is independent of label usage. So we use labels. I should change that. Use a level of significance of alpha equal to 0.05. Okay, and the data is from. So I'll state that again. Use a level of significance of alpha equal to 0.05, and the data from the study are summarized in the following table. Okay. So out of 296 women, 63 are label users, and out of 251 men, 27 are label users. So step 1 is state the null and alternative hypotheses. The null is that gender and label usage are independent. Okay, so you have to state specifically what the row variable and the column variable are. Step number 2 is gender and label usage are not independent. Okay. So then step number 2, and step number 2, you calculate this either using Excel or SPSS. Now what I have here is an example of SPSS output, and then this is the test statistic. There'll be a similar table in Excel, but the test statistic, this is the test statistic here. Degrees of freedom is 1, okay, and that's going to step number 3, which is number of rows minus 1 times the number of columns minus 1. If you go back, I'm going to go back a couple of slides here. The number of rows, you don't include the totals, but it's yes, no, those 2 rows, women and men, those are 2 columns, so 2 minus 1 times 2 minus 1 is 1, and that's the degrees of freedom. However, in your SPSS or Excel output, you can also get the degrees of freedom as well here. Now step 4 is get the p-value. Now the p-value you can also get from Excel or SPSS, and this is the number I have here, which is 0.001. I should change that here because, well, it's close to 0, but I should be more precise. So the p-value is 0.001, and since p-value is less than the level of significance, okay, we would reject the null hypothesis. Okay, and then we have sufficient evidence to say that gender and label usage are not independent. So we go back to the alternative hypothesis when we're stating our conclusions. Okay, so then finally let's go through so I'll skip this page here. So let's go to one more problem. In fact, let's do this. I'll stop the recording and then I'll continue with this next problem in part 2 of these videos.